Alright, I think we're good to go. Everything was looking good. I keep forgetting to change the stream key on Streamlabs. So I was broadcasting to an empty stream for like 15 seconds, but I think this is the right video. Alright, so welcome back to OpenGL. This is the 39th episode, almost 40, and we're going to be continuing on with the shadows today. We'll be looking at spotlights today, and we'll be able to carry most of the concepts that we learned with the directional light over. It's practically the same as of now. We're going to make an adjustment next, or maybe in a few episodes after doing the point lights, that will make it more applicable and more realistic. Alright, so for some reason OneNote is not working, so I'm gonna have to kind of use Google Images to show this stuff. I actually don't know why OneNote is not working, but either way. We're going to be looking at spotlights, like I said. So if you need a reminder, spotlights essentially just are like point lights. However, they only project in a certain field of view. So they're like cameras. The point lights they project all around. So 360 degrees and 360 degrees. So every circle in they just project all around, where spotlights are confined to some cutoff angle. And the way we're gonna analyze the shadows for now is by creating another buffer, and we're gonna treat it kind of like what you see here, where we're gonna kind of have the plane be perpendicular to the direction of the light. And this may remind you of cameras. Or, I mean, we didn't really talk about cameras in this manner, but what all cameras are doing is it's taking the scene from a direction, and it's just getting the plane that is perpendicular to the camera. And we're going to be doing the exact same thing here, except instead of grabbing colors, we're going to use just depth values. So it'll be it will just be float values. So this is a good example right here. This is also looks something like it, but not to the. God, I really wish OneNote was working. Don't know why. But it's going to be very similar to a camera. We're going to have pretty much the same values as a camera too. We'll have an up vector in there, and this. So we'll be combining code from a few places, but we're going to be rewriting it. So we'll be using the directional light shadow code, the camera code just for the projection matrices, because in essence what we need to do here with a spotlight is create some projection matrix, and that projection matrix is going to be perspective because it has a limited field of view, and it turns out that it's going to be the exact same as a camera with the spotlight's certain position, direction, and field of view. And then we'll also be using some code from the frame buffer tutorial. I forget what number that was, but just how to get the depth of a value in a perspective projection. So we'll be looking through those concepts pretty much, and I guess I'll just hop right into it. Alright, so we'll start in light.h, and we'll go to the spotlight structure. First thing we're going to want to do is actually add the up vector. So like I said, if we go into camera.h, you'll see that the values we have camera front, camera right, and then camera up, and also position. In the spotlight, we have position, direction, and then now we're actually going to add the up vector. So up vector. So it's just going to be a GLM vec3 up. Then we're going to have our cutoff and outer cutoff, which is very similar to the camera's field of view, so zoom here. That's pretty much what this is, except we're going to have a specific value for it. And then We have our attenuation constants, which stay the same. Light values stay the same. Now, like the directional light, we have to have some near and far plane because we're using a projection here. So we'll have the bounds for the shadow. Now, unlike the directional light, we do not need a bounding region because it is not an orthographic projection. We only need a direction here because we want a perspective view from the spotlight. Alright, so we'll have float near plane and float far plane. Not sure if we have this on the camera. We do not. Oh, well, we do in the we use that the near and far values in the scene when we get the view matrix, or the projection matrix actually. Alright, and then we need our light space transformation matrix. Light space transformation. So this is GLM mat 4 light space matrix, same as the directional light. And then we want to have our FBO as well. Alright, so now we're going to create a few methods just like we did with and they're going to be the exact same as the directional light. We'll have a constructor, the render method, and then updating the matrices. Alright, so what this will be is we're going to have our constructor here. It's going to take a bunch of values. We are going to take in the position, the direction, the up vector, the cutoff, the outer cutoff, the attenuation constants K0, K1, and K2, and then the light values, which are 4D vectors, so ambient, diffuse, and specular, and then the near plane and far plane values. Alright, for render, we have everything's going to stay the same except we need to add a parameter, which is the texture index that we're rendering to, that we should activate, which is the exact same as the directional light. So we'll have a shader, the index of the light to actually render to, and then the index of the texture that will be assigned for a depth map. So unsigned int texture IDX. And then we're going to update the light space matrix method. So void update matrices. Just like that. Okay. So you can copy all of these definitions as they are into light.cpp and paste them in. And then what you can do with the render method is take the code that we already have for render and then just copy and, or you know, we'll do that once we do the constructor. Alright, first make sure to add your spotlight class or structure tags. And then for the constructor, we're going to initialize essentially every single value here. So all the parameters will just go to themselves. So position to position, direction to direction, and so on. Near plane, what's near plane, and then far plane to far plane. Alright, once we have initialized all the values, we also want to initialize the frame buffer object. So we're going to have a shadow FBO, which will be 2048 by 2048, and the bit combo will be just GL depth buffer bit. And then the body, I believe, is going to be identical to the directional light. So shadow FBO.generate, then shadow FBO.bind, shadow FBO.disable color buffer, shadow FBO.allocate and attach texture, pass in GL depth attachment as the attached type. The component, or the format, will just be GL depth component, and then the type will be GL float. And then update the matrices. Alright, as for render, you can take all the code that we have already that sets pretty much all the values and then just cut and paste it into the method with the 3 parameters now. So there's a shader, the index, and the texture index. And then we want to add a few set things because we have new values that we want to set in the shader. So we'll have the set the depth texture. So GL active texture, GL texture 0 plus texture IDX, then shadow FBO dot textures at 0 dot bind, and shader dot set int the name plus dot depth buffer. This is the thing that is different because the name has an index now, so we can't just say dirlight dot direction dirlight dot depth buffer because it's not constant. We don't know it beforehand. So name plus and then industring dot depth buffer, and then that will just be just the texture index. And then we need to set the light space matrix as well. So shader dot set mat4. Oops. Let me just check one thing. Alright. Just making sure the music wasn't too loud. I should turn it down just a tad. Alright, that looks good. It's also blasted in Groove. So, yeah. I hope it wasn't a problem. Alright, then the set mat4, the name will be name plus then industring dot light space matrix, and this is the exact same light space matrix. For update matrices, this is going to be similar to the camera now. So we'll have our projection matrix, so glm mat4 proj is equal to glm perspective, then the field of view. Now, what we pass in to our spotlight in main.cpp is over here. It's commented out, but we pass in the cosine of radians, and that's just because it's easier to determine the values in the shader. So what we want to do now is to get the degrees, so get the radian, the angle measure back for the field of view. We need to take the arc cosine of that. So the field of view will be glm a cosine of outer cutoff, because that's going to be the very outer value, because if it's in between the cutoff and the outer cutoff, there's still going to be some light going through there. So we don't want to just not render any shadows in that area. And then this will be, we need to multiply this by 2.0 float, because the cutoff only goes from the center axis or the direction vector to the bounds. So that's the field of view. Then the aspect ratio will be from the FBO, so the float conversion of shadow FBO dot height divided by the float conversion of shadow FBO dot width. So that's the aspect ratio. And then for the near value, we're just going to use near plane and then far plane. So this looks almost identical to what we do for the projection matrix in the scene class with the camera. If I can get that up over... Yeah, in process input, we set the matrices. And yeah, it's pretty much set the perspective matrix. We get the radians of the zoom. Since we go in the camera, we have the degrees of it. Then the screen width, screen height, 0.1, 100.0 has the near and far bounds. Alright, and then for the view matrix, GLM mat for light view. This is going to be the same as the camera now. So GLM look at the position plus direction, and up. This is exactly identical to the camera view matrix. And then similarly to the directional light, we're going to say light space matrix is equal to the matrix multiplication of them. So projection times light view. Okay, so yeah, a lot of this code is already written. It's just we're applying it in a different way. Okay, so that's the light class, or the new methods there. Now we have to go into scene.h and scene.cpp to create some new methods. So we have the render directional light shader, and now we want to render spotlight shader method. So I'm just going to add a comment here. Set so void render spotlight shader and pass in a shader. Now in scene.cpp, you can go ahead and copy the definition there and paste it in. Actually, copy everything. Just give me a second. Alright, let me just find all this. This is the scene class is very long, so I just need to. Alright, for render spotlight shader, it's actually going to be pretty much the same as render directional light. We have to activate the shader, and then shader.setMat for light space matrix, but this time we are passing in spotlight. Oh, I forgot to add the scene class tag. So spotlights at, we need an index, I forgot, as a parameter. Unsigned int idx is the parameter there. The spotlights at idx dot, or light space matrix. And then just make sure to add that parameter in the header file as well. Alright, that's good there. And then in scene render shader, we need to change our call to spotlights.render because it requires a texture index here. All we can do is, like with the directional light, we can just say texture idx minus minus. Just like that. now that we have our scene methods, we can move on to the shader, the actual shader code, the GLSL code. Let's actually take a look at the code that we have for the shadow so far. The fragment shader is empty, so we can, like I said last time, we're going to be able to reuse this because it's empty. With directional shadow.vs, this will also allow, we can also reuse this one. Ooh, this is wrong. Oh wait, no, it's right, sorry. I misread it. This code we can use because the only thing that's going to differ between the directional light and the spotlight is the projection matrix. When we render the scene from that, we don't care what type of light it is, because the matrix will be the only thing that differs. We're not calculating any shadows here. We don't want to see how light reflects off of a certain thing, because it just doesn't really matter here, because we only need the depth value of objects from the light's point of view. So that's why we can actually rename directional shadow.vs to just shadow.vs. And then in main.cpp, we can change the shadow shader name. If I can, yeah, we can just Duralight shader becomes shadow shader, and just update the path to assets/shaders/shadows/shadow.vs and shadow.fs, because it's going to be the same. Doesn't matter. And then just make sure to update all occurrences where we pass in the directional light shader. Alright, but we do need to write some shader code, and that's in object.fs. This is going to be our shadow calculation code. So I'm going to go above calc spotlight, and we're going to return a float calc spotlight shadow. Takes in an integer IDX for the array, vec3 norm, and a vec3 light direction. Alright, we're gonna I'm just gonna rewrite everything just to remind you guys what everything means, but there will be one difference here. So we'll have our vec4 frag pose light space. This is just the transformation to the light space. So that's going to be spotlights at idx dot light space matrix. Ooh, we do need to add that to the structure. Yeah, sorry, I forgot that. In the spotlight structure, we need to add the new values. So we're going to have our float near plane, float far plane, sampler 2D, depth buffer for the texture, and then mat for light space matrix. Just forgot to do that. Alright, so for calc spotlight shadow, what's up, Mr. King Champ? That's a good name. We're going to say the spotlights at idx dot light space matrix times the vec4 of frag pose, which is the global variable, and 1.0. Then we're going to do our perspective divide, which once again transforms it to normalized device coordinates. So vec3 proj chords is equal to frag pose light space dot xyz divided by frag pose light space dot w. So once again, this goes the range of near, far to -1 to 1. I could be wrong on this one on the near far. I'm not entirely sure what I think this is just wrong, but it just transforms it to -1 to 1. Alright, then we want to go from NDC to depth range. So proj chords is equal to proj chords times 0.5 plus 0.5, and this is from -1 to 0, 1. How much experience do I have in this? Nothing professional. This is pretty much it. I'm gonna be honest with you. This is my experience, but this is pretty extensive, I'd say. Yeah, we've been doing this for quite a while, almost a year now. But yeah, that's pretty much most of my experience within 3D graphics, at least. I've done a little bit of UI on the side, but nothing too complex. Okay. And then this is one of the next thing that we're gonna look at is the one of the improvements that we did in the last episode is that if the value is too far from the light, we're not going to return any shadow because the depth value would be greater than 1, which would always be greater than the value in the texture, which has a maximum value of 1. So if too far from light, so that's going to be if proj chords dot z is greater than 1.0, then just return 0.0. Alright, then we want to go ahead and get the closest depth in the depth buffer. That's going to be float closest depth is equal to the texture of spotlights at IDX dot depth buffer and proj chords dot xy and then dot r. Alright, now the next step that is going to be that we're going to do is we're going to linearize the depth. In the directional light, we didn't have to do that actually, because hold on. Oh yeah, we're gonna have to linearize the depth in the texture that we get from the texture. And the reason why is because with the directional light we just had an orthographic projection, so it was already linear. However, with the perspective matrix, we have to do linearization by ourselves, which is the thing that we did very briefly with the frame buffer videos. So it's going to linearize the depth. So float z is going to equal closest depth times 2.0 minus 1.0. Then closest depth is going to equal, now this is going to be a shit formula here, in parentheses we're going to have 2.0 times spotlights at IDX dot near plane times spotlights at IDX dot far plane, close parentheses, divided by, and open up another set of parentheses, spotlights at IDX dot far plane plus spotlights at IDX dot near plane minus z times then in another set of parentheses, spotlights at IDX dot far plane minus spotlights at IDX dot near plane. So you should have two closing parentheses at the end. I'll split this formula up just so you can, it's easier to read. Yeah, so this is essentially linearization, and then the last step we actually have to do is say closest depth is equal to, or divided by equals to spotlights at idx dot far plane. Alright, so this is the only different step, actually. Everything else is going to be the exact same. So we're going to have to get the depth of the fragment. So floats current depth is, current depth is equal to projchords.z, and then we have to calculate the bias. Let me just make sure so you can actually take everything from the directional light and copy and paste it over for after getting the depth of, after getting the depth of the fragment. So the calculation of the bias, so going from the max to the, or min to max, using the dot product of the normal and the light direction, and then the PCF, which is just blending the nearby, the neighbor pixels in the texture to get a more accurate and smoother shadow, just because the resolution is finite. And once again, watch the previous video for the in-depth explanation of the bias, the PCF, and then also this if statement up here if it's too far from the light. And then at the end, just return shadow sum divided by 9.0 to get the average of the values. Okay. Alright, now let's go. I'll just leave this up for a second. Alright, now on to main.cpp, where we're gonna put everything together pretty much. So we already condensed our shader into just a single shader unit. And then next we have to uncomment the spotlight, or, let's just create a new spotlight altogether. Just gonna clean up some of this here. All right, for the spotlight, we're gonna call the constructor. And we'll start with a spotlight that is just looking down on the plane from an elevated position. So it'll have a position of GLM vec3 0 in the x direction, 10 in the y direction, and 0 in the z direction. The direction will be 0.0, negative 1.0, since we just want it to look down, and 0.0, and then the up vector, it can be anything perpendicular to the down, or to the direction vector. I'm just going to choose positive 1 in the x direction. So GLM vec3, 1.0, 0.0, and 0.0. This just makes it simpler. And then for the cutoff, we're going to use what we had before. So we're going to get the GLM cosine of GLM radians of 12.5 floats, and then GLM cosine of GLM radians 20.0 float. And then the attenuation constants are 1.0, 0.0014, and then 0.5 zeros, so 1, 2, 3, 4, 5, and then a 7. And then for the ambient, it's going to be 0, and then the diffusion speculator can just be 1. GLM vec 4, 1.0, and GLM vec 4, 1.0. And then for the near and far, we'll just do 0.1 and 100.0. That's the same as the camera. How did I get started learning 3D graphics? This site right here. This is I'm the most a good chunk of this is coming from I don't know, from this site. It's I give proper credit, but I also do modify it quite a bit. There's no scene class in here. I'm just that smart. This is just but this is a very good this is a very good site to, if you want to get into this. I kind of designed the first part of this tutorial, like the first 10 first 18 episodes or so, around going through the first few chapters here, and then I kind of returned to it to do some advanced lighting recently. But yeah, it's a very good site. It's very comprehensive too. Joey DeVries is the messiah in my opinion. Where is he? Come on, about. Yeah, his name is Joey DeVries. Yeah, this guy. All right. So once we've constructed the spotlight, we just need to pass it to the scene. So scene.spotlights.pushback, a reference to spotlight, and then scene.active spotlights is equal to 1. And this is just, once again, the switch, so where the value at index 1 is just, or index 0 is just 1, so that means it's active. And this is the only spotlight. Alright, now into the main loop. We're going to, after we render the directional light, or render the scene in the directional light, we want to render the scene to the spotlight. So we need to iterate through each one. So for unsigned int I is equal to 0, I is less than, and then len is equal to scene.spotlights.size. I is less than len I++. The reason why I'm creating a separate variable is just so we don't have to call the function every iteration. Then if states is index active, a reference to scene.active spotlights, and then I. Then we're just going to say scene.spotlights at I.shadow fbo.activate. This is pretty similar to the directional light now. And then scene.render spotlight shader, shadow shader. And then render scene and pass in the shadow shader. So the code inside here, these 3 lines are identical, except we're just taking a different light. And this loop here is just so it can be generalized if we choose to have more spotlights. But I could very well just keep it to just spotlights at 0, just dot activate, and it would be the same since we only have one. Okay. We didn't even call this calculation method in the fragment shader. In object.fs, we need to make sure to actually call the function, because that'd be a bummer if we just didn't do that. So after we apply attenuation, before we return, we're going to get the shadow value. So float shadow is equal to calc spotlight shadow. I misspelled that. And we're going to pass in 3 parameters here: IDX, norm, and light direction. And then return the vec4 of ambient plus, and then in parentheses, 1.0 minus shadow. And then that times, in parentheses, diffuse plus specular. So this code right here, this line is the same as the direction light. And just for a recap, if the object is in the shadow will be 1, so it will not render any diffuse or specular light. It will just be the ambience. And then if it's not in the shadow, it's going to be a 0. And then it will just render the light normally. And then otherwise, if it's blended, when it is blended, it will be concept or mathematically partially in the shadow. Okay, let's run this. We didn't update the queue positions, so this might not actually give us anything cool, but we can see, build error is good. Ooh, I forgot to pass in an index to render spotlight shader. So scene.render spotlight shader has taken the shadow shader and then the index I. Alright, oh shit, that's not right, I don't think. Hold the phone, hold the phone. Let's go into process input in the main class, in the main file, and remove any code that updates the spotlights. Yeah, okay. Alright, yeah, that was a problem. Because it was attaching it to the camera, even though I don't want it to be attached yet. Okay, so look at that. We got a shadow. Very cool. And the direction, light, shadow, same thing. And you can see that this is kind of just projecting it onto here. I guess there's... not sure what's making this big of a shadow. Where's this? Alright, I'm gonna add a few queue positions just so we can kind of have a reference for where stuff is. Or change a few. So I'll change the last 2. One will be 0.0, 11.0, and 0.0, and then another one will be 0.0, 5.0, and 0.0. Alright, so this is that's the cube that's down there, and then this is the cube where the spotlight is displaying from. Not sure what this, because there's nothing that should not be. I don't even know what this is. Huh. Okay, I think It's looking at something weird here. Oops. Let's try turning it off. Okay, yeah, turning it off works. Which is expected, but let me try not doing the directional light right now. Okay, same shit. Hold on. Okay, I think I might know what the problem is, because I was seeing the ball shadow after. So maybe this position is weird. 0, 10, 0, 0, -1, 0, 1, 0, 0. Huh. This is very irregular. Alright, directional light, that's just the same. Maybe I'll try rendering it to a depth map. That's gonna be a lot of work. Or, you know what, no it isn't, because we had it. So let me take the spotlights, move it up here. Alright, you guys don't have to do this, I'm just using some of the code from last time, just to render the depth map. No, it's not that shader that we want to use. It's the buffer shader. Okay. God. Oh, I didn't generate an instance. Alright, that's why. Alright, that looks right because you can see the... Yeah, that does look right. Because you can see the box that's right below it. It was very faint. I don't know if you guys could see that. Huh. Alright, I'm gonna check the shader math again. Could be something wrong in the object.fs, because that did look right. Okay, start at the top in main, or let's actually go to the structure to make sure everything is right there. Position, direction, cutoff, outer cutoff. Ambient, diffuse, specular, K0, K1, K2, near plane, far plane, depth buffer, light space matrix. Perfect. Alright, calc spotlight shadow now. Vec 4, frag, pose light space. Yep. Perspective divide. Go to the depth range. If it's too far, return to 0. Get the closest depth. Yep, and then the linearized depth, this could be the thing that's wrong. Okay. So float z is equal to closest depth times 2 minus 1. Closest depth is equal to 2 times the near plane times the far plane divided by far plane plus near plane minus z times the far plane minus near plane, and then that whole thing divided by the far plane. Damn it. That looks right. Ooh, okay, I got it. Yeah, it's when we're getting the texel size, we're taking the texture size of the directional light. We just forgot to update that. This is why you never copy and paste. So spotlights at IDX, and then also in the for loop when we call directional light dot depth buffer, just change that to spotlights at IDX. All right, now let's run this normally. So if you have the map, just deactivate that. And now let's run this. Et voila. Looks nice. Looks pretty good. I like it. That looks right. There's no shadow on this cube. However, there is a shadow on the plane because, yeah. Okay, let's do a little experiment here. Let's try kind of attaching, and I'm putting this in quotes because we're not really attaching it, but let's try attaching the camera to the spotlight, and by that I just mean the spotlight's direction and other values will be pretty much the same as the camera. So in the spotlight constructor, instead of calling the first 3 values, we just want to change it to cam.camera pose, cam.camera front, and then cam.camera up. And then in the update or process input method, we want to update the flashlight here, so we can uncomment, or we can just say scene.spotlights at 0.position is equal to scene.getActiveCamera.camera pose. The direction is equal to the camera front. Then scene.spotlights at 0.up is equal to scene.getActiveCamera.camera up. And then don't forget to update the matrices. So scene.spotlights at 0.update matrices. Alright, let's run this. Alright, so we have, that's our directional light, and this is our spotlight now. And you might be thinking, oh, why don't we see any shadows? Well, we should not be seeing a single shadow. And the reason why is because if we're rendering, think about what we're doing with shadow mapping. We're rendering the values, we're rendering the scene from our point of view, from the camera's point of view. And if it's not, if the object is not in that, or not directly in that view, then we render it in this shadow. And that's what we're doing with shadow mapping. And with the camera, we're essentially doing the same thing. We're just not giving a value, we're not rendering a value with its color if it's not shown, if the depth value is greater than what's in the depth buffer. So right now, we should not be seeing any shadows because they're the same thing, where we're kind of combining the two. This is a good a very good example of just shadow mapping in general. And you can also see the effects on the existent shadows and how it kind of lightens them up. You can see it really here, like that. Because when there's no directional light, then there's nothing, and no spotlight, there's nothing. But when we move the spotlight on, it kind of starts to gain a little bit of color. So yeah, that's spotlight shadows. Pretty fun stuff. Next time we're going to be doing, next time we're going to be doing point light shadows. And I do need to say one thing first. There is a limitation to this. The outer cutoff cannot be more than 45 degrees. And the reason why is because if it was more than 45 degrees, this is more about the texture, the cube map, because with the point light, we're going to be rendering it as a cube, or into a cube map, because we need 6 textures, one on each side. And each texture will have a field of view of 45.0 degrees, or of 90, sorry, so and half of 90 is 45. So if we were to think of the spotlight, or the point light, as being 6 spotlights just pointing at each face directly, then we would need they could each have a maximum of 90, where a plane would still be effective in actually rendering something, and it would give accurate calculations. But we will actually create a hybrid model of that once we do the point light, and integrate a cube map into the spotlight if necessary. Alright. Yeah, I don't really have anything else to say about spotlights. We just pretty much took a bunch of code and then that we already have, and then applied it to a new concept, which is pretty cool. But yeah, next time we'll be doing point lights, which is going to use cube maps, and we'll look at the concepts there. It might be 2 videos, I don't know. But anyway, hope you guys enjoyed. Hope you learned something, and I will, one sec. And I'll see you next time, which is probably going to be next week. So until then, stay safe, enjoy yourselves, and have a good one.